Why hello lovely humans, Jen Foxbot here. Welcome to another edition of Math Mondays. Yeah! Alright, today's episode we are going to talk about space travel. Yes, so fun. But before we get to that, I have to make a really important pitch. So it takes a lot of time and effort to do these videos, and I love doing them, but unfortunately I really need to find a way to fund that time because I have to support myself and my dog. And so if you like these videos and you value the content that I'm creating, please contribute to my Patreon account. I'll have a link in the description below so that you can click on that and easily figure out how to contribute. But without your support, I might not be able to do these. I would love to keep doing them, so please show me that you care by helping to fund my time. Thank you for listening to my pitch, and now let's dive right on in. So, one of the ways that we travel through space is using what are called ion thrusters. So NASA has been using these for long-term space travel because one of the issues in traveling in space is that there aren't any gas stations. So if you run out of fuel, you're kind of stuck, and that's very bad. So what is really beneficial about ion thrusters is that they have what is called a high impulse ratio, meaning that the amount of thrust versus the consumption is very high. So for very little consumption, you get a lot of thrust, relatively speaking. The way that these work is also really cool. So with an ion thruster, you have a chamber that is filled with some sort of gas. The most common type of gas, these are little gas molecules. The most common type of gas is xenon because it is pretty inert, meaning it's not going to explode or do anything dangerous. Again, super important for space travel. What happens is that a beam of electrons is, I'm going to get a different color here, is shot into the chamber, and the electrons collide, boop, with these little gas molecules. And what happens is that the electrons transfer their energy to the electrons around those gas molecules, and they cause some of the electrons to come off. So then you have a positively charged gas molecule, or an ion, and some freely floating electrons. And so this is happening like billions and billions and billions of times. So you have a lot of positively charged ions. This creates a plasma. And then what happens is there's a really high voltage on this side over here, which attracts these positive molecules. And so the positive molecules end up going streaming out the right side, or whatever side this happens to be, on your ion thruster. And then this is going to be at the back of your spacecraft. So these ions are then basically shot out the back of your spacecraft, and your spacecraft is like, woohoo, we are going forward. So let's see if I can draw an arrow. Yay! So the ions go that way, and your spacecraft goes this way. So how much thrust do we actually get? Well, if you were to feel it on your hand, it would actually feel like holding the weight of a piece of paper. So not very much. The maximum amount of thrust that has been achieved with an ion engine is about 91 millinewtons, which equals 91 times 10 to the negative third newtons, or 0.091 newtons. So very small. Cute. But still not trivial, especially if you don't need as much fuel as you would with a jet engine. So super important. Okay, so with this tiny amount of thrust, tiny but non-trivial amount of thrust, how fast can we actually go? Well, one of the benefits of traveling through space is that there's no air resistance. Woohoo! So there are some issues that happen with air resistance, and it can make traveling on Earth really problematic. So without any air resistance, for example, you don't have to deal with as much heat. There is going to be a little bit of resistance in space, but not anywhere close to what we're dealing with on Earth. So how fast can we go in, say, a month? Well, okay, we need some more information. One of the fun things about physics and engineering in the real world is that you're not always given all of the data that you need and you have to go and find it. So in doing research for this, I found that the NASA engineers were talking about, well, it would take 4 days to get to 60 miles per hour. Okay, so that's a decent starting point. So the amount of time is 4 days, and our ending velocity, or V final, would be 60 miles per hour. So if we wanted to do a very rough approximation, we could say, well, okay, acceleration is just change in velocity over change in time. We're doing an approximation here. Or V final minus V initial over T final minus T initial. That's going to go to 0, that goes to 0, and so we're just going to get 60 miles per hour divided by 4 days, which is 15 miles per hour per day. So these are some kind of funky units, but it still has the proper units of, we have distance per time squared. So we have hours and days, which like the physics part of my brain cringes a little bit, but the engineer part is like, it's fine. Okay, so that's a very, very rough approximation, and we actually just took the NASA engineer's word for it rather than actually taking the thrust and calculating an acceleration. So let's do this a little bit more rigorously. Okay, but to do that, we are going to have to know the mass of our spacecraft. So let's say that we want to figure out the speed of the spacecraft Dawn, which is a recent spacecraft that NASA launched so that it could go orbit an asteroid and a dwarf planet, which has never been done before. Super exciting because it means we get to see them up close. Yay! Or at least Dawn gets to see them up close, and then we get to see the radio transmissions, but still, we get images and data, which is really useful. Okay, so the mass of the Dawn spacecraft is 1,217 kilograms. I do want to note that about 425 kilograms is due to the xenon propellant. We are not going to take this into account. We're going to assume the mass stays constant, which isn't actually true, because as we are moving, we are using some of this propellant. And so this mass will decrease, and that will decrease the mass of our total spacecraft. We're going to neglect that because we're not NASA engineers. We're just trying to figure out approximately how fast our spacecraft is going to go. So, okay, we can use our handy dandy Newton's equation, F equals mass times acceleration, or force equals mass times acceleration. We plug in this, we solve for A, and we end up getting an acceleration equal to 7.5 times 10 to the negative fifth meters per second squared. Ha, LOL, that's really, really, really tiny. But you know what? That's okay, because these ion thrusters are going to be on all of the time. So if we leave this on for an entire day, that's a lot of seconds. In fact, one day equals 86,400 seconds. I'm going to put that as an aside. So if we want to figure out how fast we're going to go in one day, we would just multiply, let's see, we have our equation A equals change in V over change in T. So we multiply acceleration times the amount of time to get our velocity. And so this times 86,400 is actually going to give us, this one I don't have memorized, we are going to get a velocity of 6.5 meters per second. And check this out, that's actually 14.5 miles per hour. Ha, look at that. So our first initial rough approximation was reasonable. Pretty cool. Okay, so now how fast can we be going in 30 days? I'll just write D because I want to be lazy. So our velocity is now going to be about 434 miles per hour. So that is a little bit slower than the average commercial aircraft. So then what about in 365 days in a year? With our ion thrusters on pretty much all of the time, the only exception they get turned off is when the Dawn spacecraft is signaling back to Earth, but otherwise they are on all the time, so moving forward most of the time. So in 365 days, our velocity would be 5,275 miles per hour. That's very fast. Very fast. It's actually faster than the fastest jet on Earth. NASA holds the record, surprise, surprise, and their record is 5,000 miles per hour. So in a year, our Dawn spacecraft, with this tiny amount of thrust, is going faster than the fastest jet engine, or jet airliner, whatever you would call that. Okay, so now I'm going to use 979 days. How fast is the Dawn spacecraft going in 979 days? And you're like, why do we care about that amount of time? So that is the amount of time that it will take the Dawn spacecraft to reach its first destination, or its first orbit. And so in 979 days, it would be going 14,150 miles per hour. That is very fast. And it would use that speed to get into orbit, and then it would take data of the asteroid. I'm not sure which one it's doing first, the asteroid or the planet. Cool. That's pretty rad, right? The math is actually fairly straightforward. We just have to make sure that we're gathering the right quantities and using them in the appropriate places. Again, to be more accurate, we should actually be calculating the rate of mass decrease due to the rate of consumption of the propellant. But this is a little hand wavy. That's okay. We don't have to be accurate. The engineers for NASA do, though. Pretty cool, right? I love this stuff. Please let me know if you have any questions about ion thrusters or about space in general. That was actually my specialty when I was in college. There's our clock, very fun. Or if you have any questions about other math topics, let me know and we'll tackle them together. Thanks very much for watching, friends, and we'll see you next time. Bye!